The two major driving processes behind nuclear weaponry are fission and fusion. Let's start with fission, which creates the atomic bomb. The fission process is initiated when a free neutron comes in contact with a heavy atom, usually uranium or plutonium. When this neutron hits the atom becomes unstable and splits apart into two new atoms, or fission products. At this time, more free neutrons are released, which collide with the fission products and other atoms, creating a chain reaction. This breakage results in a major release of energy. Here, we can clearly see this chain reaction process demonstrated with uranium. Uranium is the most commonly used element in nuclear fission. This is due to the fact that its nucleus is easily split apart, especially in its isotope uranium-235. An isotope is just a varying form of an atom with different amounts of neutrons. For example, all uranium atoms and isotopes have 92 protons. However, uranium-235 has 143 neutrons, and uranium-238 has 146 neutrons. Uranium-235 is generally used more in fission reactions than uranium-238 because it is less stable, so it is easier to break apart. Heavier elements, like uranium, are used because they can break apart many times, an essential part in the fission chain reaction. Uranium-235 typically releases between 2 and 3 neutrons when it is split. This means there is a high chance that it will start another reaction and initiate the chain reaction needed to create a nuclear bomb. The other major process is fusion, which creates the hydrogen bomb along with fission. Fusion occurs when two lightweight nuclei collide to form a heavier nucleus. In doing so, this process releases lots of energy, even more than fission. Fusion, unlike fission, requires lightweight nuclei, which is why two isotopes of hydrogen, deuterium and tritium, are generally combined in this reaction. This is why nuclear bombs that use fusion are called hydrogen bombs. Whether the bomb relies on fission, like an atomic bomb, or fusion, like a hydrogen bomb, an incredible amount of sound, energy, and radiation is released.
Types of nuclear weapons: atomic bombs and hydrogen bombs. The atomic bomb is powered by fission, while the hydrogen bomb is powered by fusion. While they are usually interchangeable when referred to in conversation, there is a big difference between the two. The atomic bomb is a much weaker version. Atom bombs can release up to 500 kilotons of energy, or 4 times 10 to the 15th joules, while the SAR bomb, which is the biggest hydrogen bomb ever dropped, yielded 50 megatons of energy, or 2 times 10 to the 19th joules. The blast force of the nuclear weapons accounts for about 50% of the total energy released. Now, how else is the energy released? Nuclear weapons reach ridiculous temperatures of around 100 million degrees Celsius, 4 times that the temperature of the sun. Most of the heat is absorbed by the air rapidly, but when it's detonated, it creates an enormous fireball of heat and radiation. The heat of the blast accounts for about 35% of the energy released and vaporizes anything close to it. Now, onto the question, what is radiation? Radiation is the emission or transmission of energy in the form of waves or particles through space or through a material medium. Nuclear bombs release the two strongest types of radiation, which are gamma rays and X-rays.
Effects of nuclear radiation on the body. 1 sievert dose of radiation in a day is enough to make a person feel ill. 1 to 3 sieverts leads to damaged bone marrow and organs. At 3 to 6 sieverts, hemorrhaging is added. From 6 to 10 sieverts, chances of death is around 90%. Above 10 sieverts, death is inevitable. Ionizing radiation is carcinogenic. A prevalent cancer is leukemia. This is due to the high turnover rate of bone marrow cells. Cell apoptosis. This is one of the ways radiation can kill cells. It is also known as cell death or interphase death. DNA damage is an important trigger of the apoptotic response. Cellular level. Cells are stripped from electrons, resulting in the ionization. This can lead to DNA breakage and mutations. As a result, uncontrollable cell divisions, which can lead to cancer. If DNA molecules are mutated enough, the cells cannot replicate, resulting in cell death, known as radiation-induced reproductive failure. The gamma rays that reach the cell can break the DNA apart. Two different damaging processes can occur, either single-strand or double-strand breaks. Single-strand breaks can be repaired, but these reparations are incorrect and can lead to cancer cell creation.
With regards to our research about nuclear bombs and the properties we research within them, we've come to the understanding that nuclear bombs aren't just a type of weaponry. Nuclear bombs have the ability to not only take millions of lives at an instant, but they have the ability to destroy environments for hundreds of years before being able to provide a habitat for living organisms. This is due to the bomb's thermal properties, which have long-term effects on surrounding environments. A nuclear explosion creates 10 or more calories of heat in a fraction of a microsecond. Such a high energy density leads to temperatures in the tens of millions of degrees and to a high rate of diffusion of the energy out of the bomb and through the surrounding air. Therefore, the damage nuclear bombs can cause is so astronomical, we hope that one will never be used again. Thank you.